Are you prepared to embark on an extraordinary odyssey through the boundless expanses of outer space? Brace yourself as we are poised to unlock the enigmatic secrets of the universe. And this is thanks to the James Webb Space Telescope, the most powerful telescope ever to be put into space. When the James Webb Space Telescope, or JWST, launched on December the 25th, 2021, scientists expected the telescope to reveal unknowns in the deepest realms of space. But they certainly didn't anticipate this. As James Webb opened its eyes on the universe, it showed the curtain is lifting on a new era of our cosmic story, revealing strong evidence that challenges the Big Bang Theory. These unimagined findings, as renowned physicist Michio Kaku said, could transform our understanding of the cosmos.
We have to rewrite every single high school textbook on the planet Earth.
Join us as we dig deep into James Webb's mind-bending discoveries that could defy Big Bang. Excellent evidence shows that the universe started with an event called the Big Bang, 13.8 billion years ago, which left it in an ultra-hot, ultra-dense state. The universe immediately began expanding after the Big Bang, cooling as it did so. 1 second after the Big Bang, the universe was 100 trillion miles across, with an average temperature of an incredible 18 billion degrees Fahrenheit, that's 10 billion or so degrees Celsius. Around 400,000 years after the Big Bang, the universe was 10 million light-years across, and the temperature had cooled to 5,500 degrees Fahrenheit, about 3,000 degrees Celsius. If anyone had been there to see it at this point, the universe would have been glowing dull red like a giant heat lamp. Throughout this time, space was filled with a smooth soup of high-energy particles, radiation, hydrogen, and helium. There was no structure. As the expanding universe became bigger and colder, the soup thinned out, and everything faded to black. This was the start of what astronomers call the Dark Ages of the universe. The soup of the Dark Ages was not perfectly uniform, and due to gravity, tiny areas of gas began to clump together and become more dense. The smooth universe became lumpy, and these clumps of denser gas were seeds for the eventual formation of stars, galaxies, and everything else we see in the universe. Although there was nothing to see, the Dark Ages were an important phase in the evolution of the universe. The Dark Ages ended when gravity formed the first stars and galaxies that eventually began to emit the first light. Although astronomers don't know when first light happened, the best guess is that it was several 100 million years after the Big Bang. Astronomers also don't know whether stars or galaxies formed first. Current theories based on how gravity forms structure in a universe dominated by dark matter suggest that small objects like stars and star clusters likely formed first and then later grew into dwarf galaxies and then larger galaxies like the Milky Way. These first stars in the universe were extreme objects compared to stars of today. They were 1,000,000 times brighter, but they lived very short lives. They burned hot and bright, and when they died, they left behind black holes up to 100 times the Sun's mass, which might have acted as the seeds for galaxy formation. Astronomers would love to study this fascinating and important era of the universe, but detecting first light is incredibly challenging. Compared to massive, bright galaxies of today, the first objects were very small, and due to the constant expansion of the universe, they're now tens of billions of light-years away from Earth. Also, the earlier stars were surrounded by gas left over from their formation, and this gas acted like fog and absorbed most of the light. It took several 100 million years for radiation to blast away the fog. This early light is very faint by the time it gets to Earth. But this is not the only challenge. As the universe expands, it continuously stretches the wavelength of light traveling through it. This is called redshift because it shifts light of shorter wavelengths, like blue or white light, to longer wavelengths like red or infrared light. Though not a perfect analogy, it is similar to how when a car drives past you, the pitch of any sounds it is making drops noticeably. By the time light emitted by an early star or galaxy 13 billion years ago reaches any telescope on Earth, it has been stretched by a factor of 10 by the expansion of the universe. It arrives as infrared light, meaning it has a wavelength longer than that of red light. To see first light, you have to be looking for infrared light. And that's also why engineers optimized James Webb Space Telescope for specifically detecting the faint infrared light of the earliest stars or galaxies. Compared to the Hubble Space Telescope, JWST has a 15 times wider field of view on its camera, collects 6 times more light, and its sensors are tuned to be most sensitive to infrared light. This is one of the JWST's handiest tricks. Using its infrared sensing instruments, the telescope can peer past dusty regions of space to study light that was emitted more than 13 billion years ago by the most ancient stars and galaxies in the universe. That's how JWST took its famous deep field image, and that's how it will attempt to look even further back in time to the first few 100 million years after the Big Bang. The stars that the telescope will reveal may actually be long dead today, but as their ancient light makes the lengthy journey across the universe, JWST treats our mortal eyes to a one-of-a-kind time travel display. With this data, it could lift the veil on the secrets of the universe. That's why some have called NASA's JWST the telescope that ate astronomy. It is the most powerful space telescope ever built, and a complex piece of mechanical origami that has pushed the limits of human engineering. On December the 25th, 2021, after years of delays and billions of dollars in cost overruns, the telescope was launched into space and ushered in the next era of astronomy. Now it's been more than a year since the most ambitious and most costly space telescope ever built was launched toward the L2 Lagrange point on the far side of the Earth from the Sun. Following the nerve-shredding deployment that saw its mirrors and sunshield successfully unfold while navigating 344 potential points of failure, the $10 billion JWST has been churning out fantastic astronomical data since the summer. Even less than 6 months into observation, this data is transformative, and scientists have already used it to make several important and groundbreaking discoveries. JWST was heralded as a revolutionary telescope before it launched. Now that it is in business, we look at some of the many ways that it is already succeeding in transforming astronomy. Perhaps the most spectacular and widely circulated photograph has been that of an amazing vista of distant galaxies known as Webb's first deep field. According to Bill Nelson, director of NASA, it represents, quote, a tiny portion of the universe, the size of a grain of sand held on the finger of an outstretched arm. Countless galaxies of every imaginable shape can be observed in this vanishing portion of the sky. Elongated, flattened, and round, others so bright that they overshadow their neighbors. The universe overwhelms us, Nelson said. We are unable to conceive it and imagine its immensity. Better with a photograph? There is no image that can represent it in all its greatness. But from this week, we have the closest thing. All week we have been looking with emotion at the first photo that the James Webb Space Telescope has captured. How Carl Sagan would smile today if he could have seen this image. The most distant of these galaxies, which appear as infrared arcs due to their so-called redshift and gravitational lensing, which distorts their apparent shape, emitted their light more than 13 billion years ago, according to preliminary calculations. just a few 100 million years after the moment that the entire universe was supposedly created 13.8 billion years ago, according to the Big Bang Theory. Observing more and more galaxies at times that barely succeed the supposed origin of the universe raises serious questions about the viability of the Big Bang Theory. How could bright, fully formed galaxies exist at what in cosmological terms would be regarded as a mere moment after the universe came into being? It is like watching an adult emerging fully formed from childbirth. According to the most widely accepted models of galaxy formation, giant galaxies are formed from small, faint clouds that gradually coalesce through cosmic mergers. This process takes billions of years. At a time when the universe was supposedly in its infancy, the theory predicts only the faintest dwarf galaxies, so small and faint that we would barely expect to see anything at all. Only later would giant galaxies form from cosmic mergers. And yet, here in the very first images sent back by the JWST, we are already confronted with galactic behemoths, giants that simply could not have formed in the time allotted to them in the established theory of the Big Bang. Put simply, James Webb is defying the supreme theory describing our cosmic origins. And that's not the only time James Webb has challenged our understanding. Earlier this year, the Time Machine has exposed an unimaginable finding that caused a stir in the scientific community. Specifically, while scanning a region of the cosmos near the Big Dipper, James Webb discovered a group of galaxies from the dawn of the universe that are so massive they shouldn't exist at all. The 6 gargantuan galaxies, which contain almost as many stars as the Milky Way, despite forming only 500 to 700 million years after the Big Bang, have been dubbed universe breakers by the team of astronomers that spotted them. That's because, if they're real, the discovery calls our entire understanding of the galaxy formation into question. It's bananas, co-author Erica Nelson, an assistant professor of astrophysics at the University of Colorado Boulder and one of the researchers who made the discovery, said in a statement. You just don't expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form, she said. Scientists don't know exactly when the first clumps of stars began to merge into the beginnings of the galaxies we see today, but cosmologists previously estimated that the process began slowly taking shape within the first few 100 million years after the Big Bang. Currently accepted theories suggest that 1 to 2 billion years into the universe's life, these early proto-galaxies reached adolescence, forming into dwarf galaxies that began devouring each other to grow into ones like our own. Because light travels at a fixed speed through the vacuum of space, the deeper we look into the universe, the more remote light we intercept and the further back in time we see. By using the JWST to peer roughly 13.5 billion years into the past, the astronomers found that enormous galaxies had already burst into life very quickly after the Big Bang, when the universe was just 3% of its current age. The researchers say the galaxies are so massive they are, quote, in tension with 99% of the models for cosmology. This means that either the models need to be altered, or scientific understanding of galaxy formation requires a fundamental rethink. As Nelson said, the Milky Way forms about 1 to 2 new stars every year. Some of these galaxies would have to be forming hundreds of new stars a year for the entire history of the universe. If even one of these galaxies is real, it will push against the limits of our understanding of cosmology. Surprisingly, this isn't the last time Big Bang got caught up in trouble by JWST's discoveries. Last month, researchers unveiled results from one of the biggest and deepest astronomical surveys of the night sky carried out by JWST. The effort has identified 6 new universe breakers. From within the first 650 million years after the universe was born in the Big Bang, they are some of the earliest galaxies ever seen. and the findings have been dazzling astronomers, revealing that stars and galaxies were forming and evolving much earlier than anyone had suspected. In other words, JWST is finding more structure early on in the universe than anyone had expected. As Kevin Hainline, an astronomer at the University of Arizona in Tucson, said, "I did not expect to see these types of objects at all in our data." Observations preceding those of the JWST were already filling some astronomers with niggling doubts. In 2016, the galaxy GNZ11 was discovered. According to established theories, its light would have been emitted 13.4 billion years ago, a mere 400 million years after the supposed origin of the universe. In astronomical terms, 400 million light-years is a sigh. In 2020, the oldest black hole yet observed was discovered at 12.8 billion years old. But how could a black hole arise at a time when matter was supposedly as yet too diffuse to cause gravitational collapse? Becky Schmethurst, a junior researcher at the University of Oxford and a specialist in black holes, says, "Let's assume the very first stars formed black holes around 200 million years after the Big Bang. After they collapsed, you've then got about 13.5 billion years to grow your black hole to billions of times the mass of the Sun. That's too short a time to get it that big just with accretion." Again, it was only in 2021 that the galaxy BRI 1335-0417 was discovered, a spiral galaxy 12.4 billion years old, about a billion years earlier than the time thought possible to form this type of complex galaxy, according to the Big Bang Theory. We have discovered mammoths in the universe at a time when it seemed like they shouldn't exist. Now we need more data to know how they got there, said physicist Guillermo Borro of the University of the Pacific. The JWST promises to shed further light on these questions, but we predict that new data will only create further problems for the proponents of the Big Bang Theory. It is still early days, and much more rigorous analysis is necessary to confirm the initial observations. But some already believe that the JWST has imagined the oldest galaxies yet discovered, Glass Z11 and Glass Z12, dubbed glassy. According to preliminary analysis, these galaxies formed just 300 million years after the Big Bang. By comparison, our planet is 4.5 billion years old, and it takes 200 million years for our galaxy, the Milky Way, to complete just one rotation. The classical theory of galaxy development cannot explain how these galaxies might have formed in such a short time, and this is just the beginning. Other pre-publication papers are making claims of having identified even older galaxies. In the words of one science journalist, "In fact, astrophysicists are already finding the early universe might be a lot busier than they expected. Stars may have started forming at a much faster rate than some models have predicted. How did matter coalesce and start to form these galaxies early on? We don't know yet, but Webb is, seemingly, already rewriting what we thought we knew about the beginning of, well, everything." Referring to glassy, the same article continues, "Astronomers are basking in the possibility of glassy, which, on top of being a potential record breaker, is also far weirder than they'd imagined. Astronomers have always thought that galaxies couldn't have gotten very big so early in the universe's history and would start bulking up on stars about 500 million years out from the Big Bang. But glassy is extremely luminous, suggesting that it holds an abundance of stars, which together are 1 billion times as massive as our Sun. It isn't just the size of these galaxies that poses a problem to the established theory, so too does their composition. The stuff they are made of typically suggests it has been recycled over many generations of star formation. Big Bang theorists calculate that after the initial explosion that created the universe, all that existed was hydrogen and helium and tiny amounts of heavier elements. But we already find a surprising abundance of heavy elements and dust, produced in earlier stars in these early galaxies. Again, in the words of a scientist studying such early galaxies in 2020, quote, "From previous studies, we understood that such young galaxies are dust-poor. However, we find around 20% of the galaxies that assembled during this early epoch are already very dusty, and a significant fraction of the ultraviolet light from newborn stars is already hidden by this dust." End quote. The question of galaxy formation, enormous agglomerations of swirling gas, dust, and stars, is only the tip of the iceberg. Observational astronomy has uncovered far, far larger structures that completely confound Big Bang cosmologists. According to the assumptions that form part of Big Bang cosmology, no cosmic object can be more than 250 million light-years wide, and yet, every year astronomers are discovering larger and larger megastructures that are billions of light-years wide. In 2021, astronomers identified a structure dubbed the Giant Arc. Although it is far too faint to be seen with the naked eye, it covers a region of the sky that spans 20 full moon diameters in length. Yet, this enormous string of galaxies is located a mind-boggling 9 billion light-years away, and is 3.3 billion light-years long. There is no doubt that the JWST will continue to discover other mammoth structures, and perhaps some that even loom larger than the Giant Arc. Light itself would take billions of years to traverse such a structure. The free-fall collapse of matter under gravity would have taken eons. These discoveries are weighing down on the Big Bang theory. There is only so long that the theory's defenders can continue moving the goalposts in the manner that they have done for decades to force observations to fit their preconceived view. Genuine science progresses as theories are devised to explain our observations. An accumulation of inexplicable observations at a certain stage demands the revision of a theory. Certainly there is a disconcerted mood among astronomers. Panic reads the title of one pre-publication paper. Right now, I find myself lying awake at 3 in the morning and wondering if everything I've done is wrong, tweeted Alison Kirkpatrick of the University of Kansas. However, the consciousness of the elites of the scientific community is quite conservative. Therefore, rather than question the underlying theory, the theory of Big Bang cosmology, they are denying galaxies their infancy. Given the evidence of galaxies almost as old as the universe itself, proponents of the Big Bang assume that early galaxies formed faster than initially theorized. There is no reason to assume that the history of the local universe was not punctuated by periods of sudden development. There may well have been one or more booms of galaxy formation. The universe abounds in abrupt and sudden dialectical processes. The attempts to adjust the birth rates of galaxies, however, have less to do with explaining the birth of galaxies and everything to do with saving a theory that is quickly coming into question in the light of new discoveries. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content like this and to always improve. And as always, thanks for watching, and we'll see you next time.
Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
How did the universe come to be? The idea that the universe began with a Big Bang is firmly entrenched in the minds of billions of people for years. But the so-called science isn't nearly as settled as most people are led to believe. Many scientists know there are big problems with the idea, and the new images from the James Webb Space Telescope just deepen concern. NASA's $10 billion time machine has discovered 6 gigantic galaxies that emerged shortly after the cosmic dawn, stunning scientists by forming at a speed that upends the current understanding of the early universe. Even the renowned physicist Michio Kaku has even broken his silence to discuss the James Webb Telescope's most breakthrough image in history. Is our understanding of the universe being transformed again? Stay tuned as we reveal the mysteries of these extraordinary galaxies and delve into the awe-inspiring revelations brought to light by the James Webb Telescope. But first and foremost, we need to understand what cosmologists know, or think they know, about the universe. After the Big Bang, the infant universe began cooling off. Within a few million years, the roiling plasma that filled space settled down, and electrons, protons, and neutrons combined into atoms, mostly neutral hydrogen. Things were quiet and dark for a period of uncertain duration known as the Cosmic Dark Ages. Then something happened. Most of the material that flew apart after the Big Bang is made of something we can't see, called dark matter. It has exerted a powerful influence over the cosmos, especially at first. In the standard picture, cold dark matter, a term that means invisible, slow-moving particles, was flung about the cosmos indiscriminately. In some areas, its distribution was denser, and in these regions, it began collapsing into clumps. Visible matter, meaning atoms, clustered around the clumps of dark matter. As the atoms cooled off as well, they eventually condensed, and the first stars were born. These new sources of radiation recharged the neutral hydrogen that filled the universe during the so-called epoch of reionization. Through gravity, larger and more complex structures grew, building a vast cosmic web of galaxies. Meanwhile, everything kept flying apart. The astronomer Edwin Hubble figured out in the 1920s that the universe is expanding, and in the late 1990s, his namesake, the Hubble Space Telescope, found evidence that the expansion is accelerating. Think of the universe as a loaf of raisin bread. It starts as a mixture of flour, water, yeast, and raisins. When you combine these ingredients, the yeast begins respiring, and the loaf begins to rise. The raisins within it, stand-ins for galaxies, stretch further apart from one another as the loaf expands. The Hubble telescope saw that the loaf is rising ever faster. The raisins are flying apart at a rate that defies their gravitational attraction. This acceleration appears to be driven by the repulsive energy of space itself, so-called dark energy, which is represented by the Greek letter L, pronounced lambda. Plug values for lambda, cold dark matter, and regular matter and radiation into the equations of Albert Einstein's general theory of relativity, and you get a model of how the universe evolves. This lambda cold dark matter, ACDM model, matches almost all observations of the cosmos. One way to test this picture is by looking at very distant galaxies, equivalent to looking back in time to the first few 100 million years after the tremendous clap that started it all. The cosmos was simpler then, its evolution easier to compare against predictions. Astronomers first tried to see the earliest structures of the universe using the Hubble telescope in 1995. Over 10 days, Hubble captured 342 exposures of an empty-looking patch of space in the Big Dipper. Astronomers were astonished by the abundance hiding in the inky dark. Hubble could see thousands of galaxies at different distances and stages of development, stretching back to much earlier times than anyone expected. Hubble would go on to find some exceedingly distant galaxies. In 2016, astronomers found its most distant one, called GNZ11, a faint smudge that they dated to 400 million years after the Big Bang. That was surprisingly early for a galaxy, but it did not cast doubt on the ACDM model, in part because the galaxy is tiny, with just 1% of the Milky Way's mass, and in part because it stood alone. But when the James Webb Space Telescope came along, our story of the universe is scrambling once again. NASA's $10 billion gamble, in full operation since last summer, has shown that galaxies formed much sooner after the Big Bang than scientists previously thought, and that some of them are unexpectedly large, absolutely brimming with stars. The findings have thrown scientists into a new reality in which their existing theories no longer apply. Everyone in the astronomy community knew that the Webb telescope was going to be revolutionary, and we had a very clear list of things that we thought Webb would totally blow our socks off about, Joel Leha, an astronomer at Penn State University, said. But the discovery of the cosmically chunky galaxies where there shouldn't be any, this was nowhere on it. No one was looking for this. Instruments like Hubble and Webb are something like time machines. When the observatories look out into the depths, they're basking in starlight that left its source eons ago and has been traveling across the universe toward us ever since. In other words, to understand the cosmic beginning, astronomers must look for the most distant galaxies. Before Webb, scientists believed that those early distant galaxies emerged at a leisurely pace. The first stars formed when clouds of hydrogen gas collapsed in on themselves and ignited. Then gravity drew the ancient orbs together into galaxies. All of this drawing together of disparate matter into massive cosmic neighborhoods was assumed to have taken at least 1 billion years. Sure, the most distant galaxy that Hubble ever spotted was unexpectedly bright for the cosmic conditions of the time, indicating a larger collection of stars than should have been possible. But astronomers didn't think too much of it then. They expected that Webb, with its ultra-powerful infrared vision, would uncover the starter galaxies that they anticipated, and that Hubble couldn't see. "Ha," said the shiny new telescope. In Webb's first weeks, as astronomers raced to find the most distant galaxies ever detected, they wondered whether the data were actually wrong. The ancient galaxies were just too big and bright. A recalibration of Webb's instruments soon showed that some measurements were off, making some galaxies appear more distant than they actually were, and some claims were revised. But the big picture findings stuck. The early universe was, somehow, bold and brash and remarkably luminous. The objects we're finding are as massive or larger than the Milky Way, which is astounding, said Leha, who co-published a paper last week that identified 6 enormous galaxies that existed just 500 million to 700 million years after the Big Bang. One of these galaxies may have a mass 100 billion times that of our Sun. Our own galaxy similarly contains many billions of stars, but it has had 13 billion years to reach its size. For a brief moment, this new reality seemed to threaten astronomers' fundamental understanding of the entire cosmos. If the starting point looked like that, could the standard model of cosmology, our strongest theory about the origins and composition of the universe, the one that didn't account for what Webb found, be wrong? But astronomers now believe that the theory can accommodate the new telescope's surprises. Recent computer simulations guided by the standard model have shown that the universe could indeed have created some of the galaxies that Webb has found. While on the face of it, the data don't seem consistent with cosmological models, I think what we're going to find is it's not cosmology that's the problem, but really what we understand about how galaxies formed, Leha said. The possible explanations for how astronomers got it wrong are plentiful. Perhaps early stars formed far more efficiently than we thought, through mechanisms that scientists hadn't considered before. Alison Kirkpatrick, an astronomer at the University of Kansas, who studies galaxy evolution, wonders whether cosmic dust in these galaxies could be playing tricks on Webb, making stars appear older than they really are, and maybe cosmic dust was just different back then. Ivo Labi, an astronomer at Swinburne University of Technology, suspects that black holes could play a role. They are among the most luminous objects in the universe when they're feeding on cosmic matter, which glows as it gets sucked in. If you dump a lot of gas into a black hole, it will start to outshine the entire galaxy, Labe said. Such black holes could make early galaxies appear brighter, more star-filled, but none of these possibilities will undo the fact that the first island universes are not what we expected. Even accounting for some weird new phenomena, everything's too big, and it's too big too soon, Kirkpatrick said. Investigating these questions will require more Webb observations, particularly the kind that yield more detailed measurements of starlight, known as spectroscopy. Astronomers need more to confirm that the most unusual galaxies they found are the real deal. And if they really are as old and big as they seem, understanding their composition will help astronomers suss out the conditions in which they formed. Researchers are in the thick of it now, with fresh spectroscopic data expected to come this spring. The effort verges on soul-searching. Primordial starlight has never been so in demand, and astronomers and theorists, those who observe cosmic wonders and those who explain them, respectively, don't know exactly what they'll find once they're finished. It's probably going to be something like 5 years until we've totally settled into our new universe that we've gotten from JWST, Ren Seuss, an astronomer at UC Santa Cruz and Stanford, said. In one sense, these new discoveries have injected drama, even anxiety, into a field that was quite stable. But in another sense, it's just fun. As Erica Nelson, an astronomer at the University of Colorado at Boulder, said, "It's incredible how the universe is just so much weirder than we thought it was. It's the beginning of the universe. It's not going to affect my life, so it's really fun to think about this kind of stuff." After all, it is clear that when astronomers discuss about what Webb has found so far, one word keeps coming up: shouldn't. Galaxies shouldn't be this way. The cosmic dawn shouldn't be that way. We find these shouldn'ts delightful. They hint at the well-intentioned hubris of humans, especially the most curious ones, those who wish to determine exactly how something works and why. But of course, the universe says, speaking to us by way of a giant telescope floating 1,000,000 miles from Earth, this is how it is. This is, apparently, how it has always been. We're just discovering the wonder of it now. That's all the information that we have for you today. Don't forget to give us a thumbs up if you've enjoyed today's episode. Subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. And as always, thanks for watching, and we will see you next time.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
On the morning of July the 11th, 2022, the National Aeronautics and Space Administration, or NASA as we know it to be, unveiled the first images captured by the James Webb Space Telescope, or again, JWST, an instrument hailed as the most powerful space telescope in history. Named after NASA's second director, the telescope underwent a 26-year development process. The patience, time, and resources invested by the scientists at NASA into the JWST have been rewarded by the cosmos. The images of distant galaxies captured by the James Webb Telescope are gradually revealing information that challenges our understanding of the universe. Could we become the Galileos of this new era? Join us today as we watch this fascinating video, and welcome to Eyes 200M, where we will embark on a journey to explore the mysteries of the universe from the dawn of time. James Webb has discovered 700 galaxies beyond the edge of the Big Bang. The first achievement announced by the James Webb Telescope is the image capturing light from the SMACS 0723 galaxy cluster. This galaxy cluster is located at a distance of 5.12 billion light-years and lies in the southern part of the constellation Pisces. It is a patch of sky visible from the southern hemisphere of Earth and is often visited by the Hubble and other telescopes in search of deep cosmic history. The initial data is of immense significance, as it reveals the structure of the universe when it was just 600 million years old, measuring from the starting point of the Big Bang. Scientists anticipate that the JWST can uncover even more about the formation or demise of stars and planets, the shape of black holes, or the existence of extraterrestrial life. The latest information has somewhat fulfilled humanity's aspirations, as the images of 700 galaxies at the edge of the universe are sent back from James Webb. The evidence captured by infrared light has caused the scientific community to pause and reassess the models of the early universe. Can humanity overcome the shock of this knowledge and construct a new cosmological model based upon these new unimaginable discoveries? That remains an unanswered question. However, we all know that, quote, "Today the ancient hidden part of the universe will reveal itself, and our understanding of the cosmos will forever be changed," said Kenneth Sembach, director of the Space Telescope Science Institute, or TSTSI. So what exactly has the JWST unveiled about the universe? It is precisely the information that humanity has been searching for ages: the genesis of the endless cosmic night with its stars. Among the 700 galaxies within the reach of JWST's observations, astronomers have discovered 6 candidates that could overturn the entire theory of cosmic formation. The entire knowledge that we have built up until now may now be flawed, as the images from JWST reveal galaxies approximately 13.5 billion years old, containing tens of hundreds of billions of stars with masses equivalent to that of the Sun, just 500 to 700 million years after the Big Bang. This means that they are comparable in size to our own Milky Way galaxy. According to a recent study published on February the 22nd in the journal Nature, the newly discovered galaxies are so large that they contradict 99% of the representative models for early galaxies in the universe. This has left scientists utterly perplexed. The current theory suggests that galaxies begin their formation from small stellar dust clouds and gradually grow over time, but new discoveries are proving the opposite. It is, quote, reversing what many believed were well-established scientific theories. Joel Leja, an assistant professor of astronomy and astrophysics at Penn State University and co-author of the research paper, stated, "These findings make the entire picture of the galaxy formation as we understand it uncertain." These 6 galaxies are not the oldest ones observed by JWST. Last year, scientists discovered 4 galaxies dating back to approximately 350 million years after the Big Bang, but those galaxies were much smaller in size. Dr. Emma Chapman, an astrophysicist at the University of Nottingham, who was not involved in the latest research, stated that further observations of other discoveries are needed before dismissing the current models of our universe. Currently, the research team is planning to gather spectroscopic images from the data sent back by JWST. This method can provide more accurate information about the age and allow for better estimates of the masses of the 6 new galaxies found. If you're interested in the latest results, please give us a like, subscribe, and turn on the notifications. EYES 200M will keep you updated and analyze the latest information for you. Now, let's delve into the hypothesis derived from the JWST discoveries. Will our understanding of star and galaxy formation change? Well, until now, the process of star and galaxy formation has remained shrouded in mystery. Erica Nelson, an astronomer at the University of Colorado Boulder, states, Each year, the Milky Way produces 1 to 2 new stars. In contrast, some of the 700 objects observed by JWST may generate hundreds of new stars annually and span throughout the history of the universe. If these findings can be verified, we will take a significant step forward in exploring and redefining the universe." End quote. We cannot rule out the possibility that these galaxies could be quasars or supermassive black holes. The new infrared images obtained by JWST will need further clarification on this matter. According to the theory describing the processes following the Big Bang, approximately 1 to 300 million years after the explosion, the first stars began to form. These were very large, bright stars responsible for the ionization process of the universe. At this time, we did not have yet elements heavier than lithium from the nucleosynthesis stage of the Big Bang. The first stars produced heavier elements through stellar nucleosynthesis. Therefore, the majority of the primordial light in the universe may be ultraviolet radiation from these very hot stars. The surface temperature of the stars also began to ionize hydrogen and neutralize helium around the stars after their formation. We refer to this event as the era of reionization. Scientists from the California Institute of Technology and the Sloan Digital Sky Survey have also found evidence for the final stage of this reionization process. They discovered strong absorption of ultraviolet radiation in the spectra of quasars at around 900 million years after the Big Bang. These findings suggest that the remaining neutral hydrogen was ionized at that time. If the stars were indeed very massive, their lifetimes would be very short, only a few million years. Some stars would explode in supernova, releasing the metals they produced. Stars with masses between 100 and 250 times that of the Sun are predicted to be completely destroyed in a powerful explosion. Most of the first stars fall within this mass range. Metals are more efficient than hydrogen in cooling the star-forming clouds and enabling them to collapse into stars, and even a small amount of metal production and release can have a significant impact on star formation. So, what is the contradiction here? If everything happened according to our previous understanding, the reionization process would occur more than 1 billion years after the Big Bang. After that, more stable stars would be formed. It would take billions of years more for galaxies to begin to appear. But now we have mature galaxies with ages as young as 5 to 700 million years old. What has happened to the theory of dark energy and the rate of cosmic expansion? Or are there still other mystery factors about matter and energy that we are yet to discover? Evidence of organic molecules in the early universe. Now, let us revisit the theory of the particle formation process to gather more evidence on how stars and galaxies were formed. According to a study published in the journal Nature in June of 2023, scientists using the JWST have discovered a cloud consisting of complex organic molecules within the galaxy SPT 0418-47, located 12.3 billion light-years away from Earth, and these are the oldest known organic molecules ever identified by humans. The spectroscopic data reveals that these organic molecules belong to complex forms, primarily aromatic polycyclic hydrocarbons, or PAHs for short. On Earth, PAHs are found in forest fire smoke and car exhaust fumes. In space, they may play a significant role in star formation. Scientists speculate that they help regulate the temperature of gas clouds in stellar nurseries, thereby influencing the timing and location of star development. PAHs are considered one of the fundamental building blocks for the longest-lasting forms of life here on Earth. What does this mean? Isn't it fascinating that these organic molecules existed in the early universe just over 1 billion years after the Big Bang? This is something that no cosmological model has ever addressed. Joaquin Vieira, a co-author of the study from the University of Illinois Urbana-Champaign in U.S., stated, quote, "We were very surprised by this discovery. It has provided new insights into the complex chemical interactions occurring in the early galaxies of the primordial universe. The detection of these complex organic molecules at such a distance is a significant breakthrough," end quote. Humanity first became aware of the galaxy SPT 0418-47 in 2020 using the South Pole Telescope of the National Science Foundation. The mass of the stars could only be determined through a physical trick called gravitational lensing. This effect occurs when light from a distant object is curved around a nearby massive object due to its gravitational force. During this process, the distant light is distorted and magnified, and in the case of SPT 0418-47, scientists calculated that it appeared over 30 times brighter. During the analysis of this light, initial findings indicate that SPT 0418-48 contained a significant amount of heavy elements. However, the South Pole Telescope was unable to provide a clear view of its carbon-containing organic components due to inadequate wavelengths. Thanks to the JWST, though, everything is much clearer now. Justin Spilker, an astronomer at Texas A&M University and the lead author of the study, stated, quote, "Everywhere we look, we see molecules associated with forming stars. This supports the hypothesis that organic molecules aid in the birth of stars," end quote. However, what remains puzzling is the uneven distribution of PAH cloud densities. This still remains an unanswered mystery for us all. SPT 0418-47 exhibits several similarities to our own Milky Way galaxy, which is unusual for an ancient galaxy. Galaxies from the early universe are typically thought to have different shapes compared to those observed today. Francesca Rizzo, a researcher at the Max Planck University for Astrophysics in Germany, stated, "This discovery represents a breakthrough in the study of galaxy formation, revealing that the structures we observe in nearby spiral galaxies and in our Milky Way even existed 12 billion years ago," end quote. I cannot express enough how remarkable this finding is. We can utilize these studies to determine the time frame in which the universe and galaxies formed. It is possible that in a distant place, billions of light years away, a civilization similar to Earth was formed and continues to exist today. This is truly awe-inspiring. Conflicts regarding the formation of galaxies. According to our current theories, there are two ways in which galaxies form. The first model asserts that giant elliptical galaxies are formed through the rapid collapse of dark gas and matter. During this process, most of the dust clouds quickly transform into stars. Subsequently, galaxies only undergo slow changes as stars evolve. This scenario is referred to by astronomers as the top-down process. The second model demonstrates that giant elliptical galaxies are primarily formed through the merging of smaller galaxies. They undergo a transformation of their gas content as stars form, following a bottom-up scenario. These observations, when considered together, suggest that the giant elliptical galaxies we observe today are formed through a combination of both top-down and bottom-up mechanisms. In the case of the largest galaxies, formed within the densest matter clusters, both processes occurred early and rapidly in cosmic history. However, both hypotheses for galaxy formation assume that they occurred billions of years after the Big Bang. At that time, the universe was at least 9.8 billion years old, with dark energy causing the expansion rate to be slower and more stable. If the evidence for the earliest galaxies from the James Webb Telescope is accurate, we will have to reconsider our models. It is possible that we will develop new theories about dark matter. But what is evident here is that the expansion rate of the universe could be significantly higher than the speed of light. Despite significant efforts, humanity still does not fully understand the majority of the knowledge related to dark matter and dark energy. This is the greatest variable that affects cosmic research and exploration. To address this issue, NASA and the U.S. Department of Energy plan to establish the Joint Dark Energy Mission, or JDEM, the first program created to study dark energy. However, the JDEM project did not receive funding, which is extremely regrettable. Why and how does dark energy relate to the formation of galaxies? This is a long and complex story. However, if you're interested, please follow and comment and let us know. In addition to providing the latest information from scientific journals, we are also delighted to assist you in exploring other interesting and fascinating areas of astronomy. Thank you for watching this episode today. We look forward to seeing you again in upcoming issues.
We are going to discover incredible things that we never imagined. The handiwork of God as we peer back in time over 13 billion years ago, capture the light from the very beginning of the creation.
The Big Bang is widely believed by most scientists as the main theory that explains the origins of the universe, how everything was made, including the stars, the planets, and everything that lives on those planets, like us. Even though it's a bit of a silly name for such a huge event, the Big Bang definitely describes what it might have been like. At first, there was nothing but densely packed particles, all crammed into a space smaller than a pinhead. From this single point, a huge explosion of matter occurred, known as the Big Bang. That's just a quick summary of what happened over billions of years. However, despite the continuing popularity of the theory, essentially every prediction of the Big Bang theory has been increasingly contradicted by better and better data. For that reason, when NASA launched James Webb, the largest and most powerful space science telescope ever built into space, scientists expected the telescope's data would support the Big Bang theory. Sadly, after just 1 year in space, the Webb telescope is blowing scientists away with its keen eye on the universe. The $10 billion gamble has captured unprecedented images so far back in time, revealing the existence of galaxies so old that could shatter all we've known about the very origins of the universe. Join us as we dig into the James Webb Telescope's terrifying discovery before the Big Bang. The story begins when we have a groundbreaking new view of the cosmos from the James Webb Space Telescope, a view the world has never seen before. Astronomer Rohan Naidu was at home with his girlfriend when he found the galaxy that nearly broke cosmology. As his algorithm dug through early images from the James Webb Space Telescope, JWST, late one night in July 2022, Naidu shot to attention. It had sifted out an object that Naidu recognized was inexplicably massive and dated back to just 300 million years after the Big Bang, making it older than any galaxy ever seen before. And that was such a huge shock to him that he had to call his girlfriend over right away and told her, "This might be the most distant starlight we've ever seen." After exchanging excited messages with one of his collaborators, with lots of exclamation marks, Naidu got to work. Days later, they published a paper on the candidate galaxy which they dubbed Glass Z13. The internet exploded. It reverberated around the world, Naidu said. The discovery of this galaxy, just weeks into JWST's full operations, was beyond astronomers' wildest dreams. JWST, the largest, most powerful observatory ever launched from Earth, was built to revolutionize our understanding of the universe. Stationed 1.5 million kilometers away from earthly interference and chilled close to absolute zero by its tennis court-sized sunshade, the telescope carries a giant segmented mirror and exquisitely sensitive instruments that were designed to uncover details of cosmic dawn never before observed. This is a scarcely probed era, no more than a few 100 million years after the Big Bang, in which the very first stars and galaxies coalesced. How exactly this process unfolded depends on exotic physics ranging from the uncertain influences of dark matter and dark energy to the poorly understood feedbacks among starlight, gas, and dust. By glimpsing galaxies from cosmic dawn with JWST, cosmologists can test their knowledge of all these underlying phenomena, either confirming the validity of their best consensus models or revealing gaps in understanding that could herald profound new discoveries. Such observations were supposed to take time. Initial projections estimated the first galaxies would be small and faint, that JWST would find at best a few intriguingly remote candidates in its pilot investigations. Things didn't quite go as planned. Instead, as soon as the telescope scientists released its very first images of the distant universe, astronomers such as Naidu at the Massachusetts Institute of Technology started finding numerous galaxies within them that, in apparent age, size, and luminosity, surpassed all predictions. The competition for discovery was fierce. With each new day, it seemed claims of yet another record-breaking earliest known galaxy emerged from one research group or another. The result, as Charlotte Mason, an astrophysicist at the University of Copenhagen said, everyone was freaking out. We really weren't expecting this. In the weeks and months following JWST's findings of surprisingly mature early galaxies, theorists and observers scrambled to explain them. Could the bevy of anomalously big and bright early galaxies be illusory, perhaps because of flaws in analysis of the telescope's initial observations? If genuine, could they somehow be explained by standard cosmological models? Or just maybe, were they the first hints that the universe is more strange and complex than ever our boldest theories had supposed? At stake is nothing less than our very understanding of how the orderly universe we know emerged from primordial chaos. JWST's early revelations could rewrite the opening chapters of cosmic history, which concern not only distant epochs and faraway galaxies, but also our own existence here in the familiar Milky Way. As JWST scientist Mark Makarian, a senior advisor for science and exploration at the European Space Agency, said, "You build these machines not to confirm the paradigm, but to break it. You just don't know how it will break." One might say JWST's observations of early galaxies have been billions of years in the making, but more modestly, they trace back to the Space Telescope Science Institute, STSCI, in 1985. At the time, the Hubble Space Telescope was still 5 years away from launching on a space shuttle. But Garth Illingworth, then deputy director of the STSCI, was surprised one day when his boss, then director Riccardo Giacconi, who died in 2018, asked him to start thinking about what would come after Hubble much farther down the road. "I protested, saying we've got more than enough to do on Hubble," Illingsworth recalled, but Giacconi was insistent. "Trust me, it'll take a long time," he said, so Illingsworth and a handful of others got to work, drawing up conceit ideas for what became known as the Next Generation Space Telescope, NGST, later renamed JWST after a former NASA administrator. Hubble would be transformational, but astronomers knew its capabilities would be limited by its observations in visible light. As light from a very distant galaxy travels across the cosmic abyss, it is stretched by the expansion of the universe, a broadening of wavelengths known as redshift. The higher the redshift value, the more stretching the light has experienced, and thus the more distant its source galaxy. Redshifts for early galaxies are so high that their emitted visible light has stretched into infrared by the time it arrives at our telescopes, which is why Hubble could not see them. The NGST, in contrast, would observe in infrared and would boast a very large and very cold starlight gathering mirror, allowing it to peer much deeper into the universe. Everybody realized that Webb would be the telescope for looking at early galaxies, Illingsworth said. That became the primary science goal. The need for the telescope was highlighted in December 1995 when astronomers pointed Hubble at a seemingly empty patch of the sky for 10 consecutive days. Many experts predicted the extended observation would be a waste of resources, revealing at best a handful of dim galaxies, but instead the effort was richly rewarded. The resulting image, the Hubble Deep Field, showed the empty spot was filled with galaxies by the thousands, stretching back to 12 billion years into the 13.8 billion year history of our universe. There were galaxies everywhere, says Illingsworth, now an astrophysicist at the University of California, Santa Cruz. The Hubble Deep Field showed that the early universe was even more crowded and exciting than most anyone had expected, offering observational treasures to those who took the time and care to properly look. Yet, impressive as Hubble's Deep Field was, astronomers wanted more. After more than 2 decades of labor at a cost of some $10 billion, JWST finally launched on Christmas Day 2021. The telescope reached its deep space destination a month later, where it would endure exhaustive testing to ensure its optimal performance. By July 2022, it was ready to begin its long-awaited first year of science observations, known as Cycle 1. Part of the telescope's early time was devoted to high-impact programs across a range of disciplines, from which data would immediately be made public. 2 of those, CEERS, the Cosmic Evolution Early Release Science Survey, and GLASS, the Grism Lens Amplified Survey from Space, independently spent dozens of hours looking for galaxies in the early universe by staring at separate small portions of the sky. Not much was expected, perhaps a slightly more ornate version of the Hubble Deep Field, but nothing more. Stephen Finkelstein of the University of Texas at Austin, the lead on CEERS, says extremely distant galaxies were predicted to pop up only after a few cycles of data from multiple programs. But much to the surprise of astronomers, extremely distant galaxies came into view immediately. Hubble's record for the most distant known galaxy had been GNZ 11, spotted in 2015 at a redshift of 11, thanks to a 2009 upgrade that enhanced the telescope's modest infrared capabilities. A redshift of 11 corresponds to a cosmic age of about 400 million years, a point on the brink of when galaxy formation was thought to begin. But from the very first GLASS data, 2 teams, one led by Naidu in the breathless late-night discovery, independently found GLASS Z13 at a redshift of 13, some 70 million years farther back in time. In their quest for quick results, the researchers relied on redshift estimates derived from simple brightness-based measurements. These are easier to obtain but less precise than direct measurements of redshift, which require more dedicated observation time. Nevertheless, the simplified technique can be accurate, and here it suggested a galaxy that was unexpectedly bright and big, already bearing a mass of stars equivalent to 1 billion suns, just a few hundred times less than that of the Milky Way's stellar population, despite our own galaxy being billions of years more mature. This was beyond our most optimistic expectations, says Thomas O'Treu, an astronomer at the University of California, Los Angeles, and the lead on GLASS. The record didn't last long. In the following days, dozens of galaxy candidates from CEERS and GLASS sprang into view with estimated redshifts as high as 20, just 180 million years after the Big Bang. Some with disk-like structures that were not expected to manifest so early in cosmic history. Another team, meanwhile, found evidence for galaxies the size of our Milky Way at a redshift of 10, less than 500 million years after the Big Bang. Such behemoths emerging so rapidly defies expectations set by cosmologists' standard model of the universe's evolution, called Lambda CDM, LCDM. This model incorporates scientists' best estimates for the properties of dark energy and dark matter, which collectively act to dominate the emergence of large-scale cosmic structures. Lambda refers to dark energy, and CDM refers to dark matter that is relatively sluggish or cold. Even if you took everything that was available to form stars and snapped your fingers instantaneously, you still wouldn't be able to get that big that early, says Michael Boylan Colchin, a cosmologist at the University of Texas at Austin. It would be a real revolution. To understand the dilemma, a brief refresher is needed. In the first second after the Big Bang, our universe was an almost inconceivably hot and dense soup of primordial particles. Over the next 3 minutes, as the cosmos expanded and cooled, the nuclei of helium and other very light elements began to form. Fast forward 400,000 years, and the universe was cold enough for the first atoms to appear. When the universe was about 100 million years old, theorists say conditions were finally right for the emergence of the first stars. These giant fireballs of mostly hydrogen and helium were uncontaminated by heavier elements found in modern-day stars, so they possessed significantly different properties. Larger and brighter than today's stars, these first suns coalesced into proto-galaxies, clusters of gas that clung to vast, invisible scaffolds of dark matter. Gravity guided the subsequent interactions between these proto-galaxies, which eventually merged to form larger galaxies. This process of becoming, of the early universe's chaos giving way to the more orderly cosmos we know today, is thought to have taken about 1 billion years. JWST's discovery of bright galaxies in the early cosmos challenges this model. We should see lots of these little proto-galactic fragments that have not yet merged to make a big galaxy, says Stacy McGaugh, a cosmologist at Case Western Reserve University. Instead, we're seeing a few things that are already big galaxies. Some of these galaxies may be imposters, much closer galaxies shrouded in dust that makes them look dimmer and farther away when brightness-based measurements are used. Follow-up observations of Glass Z13 in August 2022 by the Atacama Large Millimeter Array ALMA in Chile, however, suggested that is not the case for this candidate because ALMA did not see evidence for the large amounts of dust. I think we can exclude low redshift interlopers, says Tom Bax, an astronomer at Nagoya University in Japan, who led the observations. Yet the lack of dust means ALMA struggled to see the galaxy at all, showing how difficult it could be for telescopes to confirm observations made by using JWST's advanced capabilities. The good news is there's nothing detected, Naidu said. The bad news is there's nothing detected. Only JWST, in this case, can follow up itself. The most startling potential explanation is that the canonical LCDM cosmological model is wrong and requires revision. These results are very surprising and hard to get in our standard model of cosmology, Boylan Colchin said, and the probability not a small change. We'd have to go back to the drawing board. One controversial idea is modified Newtonian dynamics, MOND, which posits that dark matter does not exist and that effects attributed to it can instead be explained by large-scale fluctuations in gravity. JWST's observations could support such a theory. MOND has had a lot of its predictions come true. This is another one of them, says McGaugh, who is one of the idea's leading proponents. Others remain unconvinced. So far, everything that we've tried to test MOND hasn't been able to really provide a satisfactory answer, says Jeha Kartaltepe, an astrophysicist at the Rochester Institute of Technology. One simpler possible solution is that galaxies in the early universe might have little or no dust, making them appear brighter. This scenario could confound efforts to calculate the galaxy's true masses and could perhaps also explain ALMA's difficulty spotting Glass Z13. It could be the supernova didn't have enough time to produce the dust, or maybe in the initial phases of galaxy formation, the dust is expelled from galaxies, says Andrea Ferrara, an astronomer at the Scuola Normale Superiore in Italy, who has proposed such a possibility. Mason and her colleagues suggest that, alternatively, in its observations of the early universe, JWST may so far be seeing only the very brightest young galaxies, which should be the easiest to spot. Maybe there's something happening in the early universe that means it's easier for some galaxies to form stars, she says. David Spergel, a theoretical astrophysicist and current president of the Simons Foundation in New York City, agrees. I think what we're seeing is that high-mass star formation is very efficient in the early universe, he says. The gas pressures are higher, the temperatures are higher. That has an enormous impact on the environment for star formation. Magnetic fields might have arisen earlier in the universe than we thought, driving material to kickstart the birth of stars. We might be seeing a signature of magnetic fields emerging very early in the universe's history, Spergel says. The rapid flow of scientific papers from JWST's initial observations is no fluke. When the first data started streaming down, astronomers were eagerly awaiting. People had been working on their pipelines for years, Boylan Colchin says, instead of the traditional peer review process, which can take months. Astronomers published on ArcSiv, a website where scientific papers can be uploaded after minimal review by moderators, but well before formal peer review. A new form of peer review unfolded in near real time on Twitter and other social media platforms. It's science by ArcSiv, Naidu says. The resulting frenzy was intense and surprising. I expected a lot of activity, says Nancy Levinson, STSCI's interim director, but I underestimated the amount. The result was that findings could be quickly publicized and discussed, but some fear at a cost. People were rushing things a little bit, says Klaus Pontopidin, JWST's project scientist at STSCI. The gold standard is a refereed, peer-reviewed paper. Early calibration issues with JWST, for example, may have affected some results. Nathan Adams of the University of Manchester in England and his colleagues found there could be dramatic changes, with one galaxy identified at a redshift of 20.4 recalibrated to just 0.7. We need to calm down a little bit, Adams says. It's a bit too early to say we've completely broken the universe. Such issues are unlikely to eradicate all of JWST's high redshift galaxies. However, given their sheer number, it's more likely that the early universe is different from what we predicted, Finkelstein said. The odds are small that we're all wrong. Astronomers are now racing to conduct follow-up observations with JWST. Levinson says she's currently reviewing about a dozen proposals from various groups asking for additional JWST observing time, most of which are seeking to scrutinize high redshift galaxy candidates. Considering the excitement and importance of these early discoveries, we thought that it was appropriate to ask for a little bit of time to confirm them, says Treyu, who put forward one of the proposals. Other programs are now set to hunt for distant galaxies, such as Cosmos Webb, led by Kartal Tepe, which is expected to hugely increase the known population of early galaxies by observing a wider swath of sky for hundreds of hours. We estimate there are thousands we'll be able to detect, she says. Further projects might look for evidence of those first proto-galaxies, perhaps using the explosive deaths of supersized first stars and especially luminous and energetic supernovae as markers for their existence. Some estimates suggest JWST could see as far as a redshift of 26, just 120 million years after the Big Bang, a cosmic blink of an eye. Much other work will be done to follow up the growing list of high redshift candidates. Even confirming a handful of these would be quite amazing, Naidu says. It would demonstrate we're not getting fooled. JWST has ushered in a new era of science, and despite the uncertainties, the rapid communication of new discoveries has invigorated astronomers. It's been fantastic, Treyu says. It's really wonderful to see the community so engaged and excited. Now the question is, if we can truly believe what we are seeing, is it time to reappraise our understanding of the dawn of time? We're peering into the unknown, Mason says. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
On July 11th and 12th, 2022, humanity stepped into the future. The James Webb Space Telescope, a flagship deep space observatory that can gaze into the depths of space, released its first scientific images, revealing the universe in an unprecedented light. Since then, the whole scientific community has been constantly surprised by how the telescope is revealing the missing pieces of the universe in the distant past. Look at breathtaking images taken by James Webb. We see a lot of galaxies that are simply too massive to exist, black holes that have grown too large too soon, strange emissions from the dawn of time, and tiny galaxies that house monster black holes. All of them are just beyond what's possible. And that's also where the trouble comes in. Once again, cosmologists were confronted with observations that are impossible to explain according to our best model of how the universe evolved. Not enough time had elapsed to have brought together that amount of matter and turned it into this many stars. The universe at this time simply had not existed long enough for black holes to bulk up to 1 billion solar masses. Thus, based on our general understanding of how galaxies and black holes form and grow, the supergiant old structures captured by James Webb should not exist. At the time, scientists argued that the scenario posed a serious challenge to cosmic history that cosmologists have yet to unravel. So, what do the new James Webb images really show? Does the conventional understanding of how the universe works need to change? Or may the universe actually be twice as old as scientists suspect? Join us as we dig deep into how ancient, gigantic structures captured by James Webb could remake all cosmic rules. One of the most common misconceptions of the Big Bang theory pertains to its very definition. Rather than being a theory of the universe's origin, it's a theory of what happens after the moment of creation. For most of the past 2,500 years, the universe was believed to be timeless and unchanging. Stars twinkled forever. They were not born. They did not evolve. They did not die. They did not even change their positions in space relative to each other. The dawn of modern astronomy came and went. Though beliefs around the movement of stars changed, and it was understood that local details might get altered in any random corner of the cosmos, the universe, as a whole, was considered permanently unchanging. Even Albert Einstein assumed that the universe now must look like the universe 1 trillion years in the past and future. Then, in 1928, discoveries by an American astronomer caused this surety to waver. Data from Edwin Hubble's telescope appeared to show that galaxies were, in fact, all rushing apart, avoiding one another as if they had the plague. Jesuit astronomer Georges Lemaitre drew a different conclusion from Hubble's observations. He believed that Einstein's theory of general relativity could be used to show that the galaxies weren't moving apart through space. On the contrary, it was space itself that was expanding, and the galaxies were simply being carried along with it. Lemaitre noted that the universe may have existed in a pre-expansion state. He described this state of the universe as a primeval atom, existing for immeasurable aeons before it was somehow set in motion. Alternative theories were floated by astronomers keen to resurrect a timeless picture of the cosmos. This included a model by Fred Hoyle, a British astronomer, who ridiculed the idea that the universe's expansion began all at once, in what he deridingly coined a Big Bang. Then, in 1964, a truly revolutionary discovery was made. Two astronomers, Robert Wilson and Arno Penzias, were using a radio telescope designed to examine satellite communications. They encountered a strange phenomenon. When they directed their telescope at any point in the sky, they found a weirdly persistent microwave signal. There was no point in the sky from which this signal did not emanate. They began to look closely at the idea that the universe had been very different in the past than it was now. This was implied by Lemaitre's idea, and had been picked up in the early 1950s by two physicists, Ralph Alpher and George Gamow. Alpher and Gamow were building a model of cosmic history where the universe began in an incredibly hot, dense state. Gamow's models predicted that, approximately 300,000 years after the universe started expanding, space filled with a particular kind of electromagnetic radiation as matter particles cooled and changed their interactions. Not only that, this radiation would persist forever, a kind of fossil light. And it was this fossil light that Wilson and Penzias inadvertently picked up in their radio telescope. All the pieces of the jigsaw were perfectly slotting together. Wilson and Penzias had made an insurmountable breakthrough. The universe did indeed have a history. It had once expanded from a type of primeval atom, and it had continued to expand since. In doing so, it had left behind traceable electromagnetic emissions, which silently polluted the sky, invisibly goading desperate researchers, waiting to be found by technology that was advanced enough. This discovery, known in scientific circles as cosmic microwave background radiation, established cosmology as a science and the Big Bang theory as the foundation for all explorations of cosmic evolution. Since then, observations have further supported its veracity, and more details have bulked out the theory. And with these, the James Webb Telescope enters the story. To be a successful theory of cosmic evolution, the Big Bang must explain all aspects of how we got from back then to now. How did that transition occur? When and how did the cosmos start to form all the structures we see today? When did the first stars form? And when did the first galaxies form? Using ever more powerful supercomputers to simulate cosmic history and ever bigger telescopes to test the results of those simulations, researchers have developed a remarkably complete story. One of the most important aspects of that story is how stars and black holes began forming before galaxies did. The explanation for this is termed hierarchical structure formation, a sub-theory, if you like, of the Big Bang. Smaller structures, like stars, form first, it says, which then collect to form larger structures, like galaxies. Many of this sub-theory's predictions were confirmed by the Hubble Space Telescope, which could look back to the era of galaxy formation. But Hubble's telescope had limitations, and astronomers needed to push back even further in time. Then, the recent years along came James Webb. A powerful space telescope was built to see the first generation of stars emerging just a few 100 million years after cosmic expansion began. Excited astronomers watched and waited for the telescope to confirm their predictions, and then it didn't. Instead of showing the formation of just a few small stars, which would satisfy the timeline of the hierarchical structure formation theory, the telescope is now sending back data that poses serious difficulties for the modern creation myth. As it looked deeper into space, the telescope revealed anomalies that challenged long-held prejudices about the origin and development of the universe, and shedded a brilliant light on profound and important scientific and philosophical questions. Indeed, you see, galaxies taken by James Webb had existed far before anyone had expected them to. In other words, somehow the universe is building galaxies earlier and faster than our theories predict. And this was no minor discrepancy. The finding is akin to parents and their children appearing in a story when the grandparents are still children themselves. Another way to imagine, it's like going to a nursery to visit your newborn and finding a room full of teenagers. And that's really disturbing, to say the least. So, what did this mean for the history of the universe? Frankly, Webb's discovery could have significant implications for cosmology, as it implies that current theories about the formation and evolution of galaxies could be incorrect or incomplete. To explain the existence of these galaxies, scientists may have to revise models of the universe's evolution and galaxy formation processes. One possibility is that these massive galaxies formed differently from the galaxies closer to us. For example, there may have been an unknown mechanism until now that allowed the formation of massive galaxies in a short period of time. Another possibility is that these galaxies are the result of exceptionally rapid mergers between smaller galaxies in the early universe, which would also require a revision of current models. In any case, the discovery made by the James Webb Space Telescope represents a significant advancement in the study of cosmic evolution and galaxy formation. This finding is likely to prompt astronomers to develop new theoretical models and seek more observational evidence to better understand the history of the universe and the properties of these enigmatic, distant galaxies. But note that the impossible massive galaxies were not an isolated incident. There have been other recent occasions in which the evidence behind science's basic understanding of the universe has been found to be alarmingly inconsistent. Take the matter of how fast the universe is expanding. This is a foundational fact in cosmological science, the so-called Hubble constant. Yet scientists have not been able to settle on a number. There are two main ways to calculate it. One involves measurements of the early universe, such as the sort that the Webb is providing. The other involves measurements of nearby stars in the modern universe. Despite decades of effort, these two methods continue to yield different answers. At first, scientists expected this discrepancy to resolve as the data got better. But the problem has stubbornly persisted even as the data have gotten far more precise. And now, new data from the Webb have exacerbated the problem. This trend suggests a flaw in the model, not in the data. Two serious issues with the standard model of cosmology would be concerning enough. But the model has already been patched up numerous times over the past half-century to better conform with the best available data. Alterations that may well be necessary and correct, but which, in light of the problems we are now confronting, could strike a skeptic as a bit too convenient. Physicists and astronomers are starting to get the sense that something may be really wrong. It's not just that some of us believe we might have to rethink the standard model of cosmology. We might also have to change the way we think about some of the most basic features of our universe, a conceptual revolution that would have implications far beyond the world of science. After all, while stunning observations made by James Webb pose serious challenges to our standard model of cosmology, it's also great news. This is what should happen in science. New data should challenge our theories and force us to confront false assumptions we hadn't even known we'd made. The James Webb Telescope has done that for cosmologists. And as more data pours in, there are no doubt going to be a lot of happy, sleepless nights as scientists try to understand exactly what the telescope is telling them about the early cosmos. And while astronomers grapple with James Webb's discovery of early galaxies, our universe is expanding at an ever-accelerating rate. This is a phenomenon that all theories of cosmology agree upon, but none can fully explain. For this observation to fit with the main theory of cosmic evolution, physicists assume that the universe is filled with an enigmatic substance dubbed dark energy that drives the expansion. But this elusive form of energy does not manifest itself in any other way, leading many astrophysicists to question its existence and explore the possibility of an alternative cause for the universe's expansion. In a new study published in the Journal of Cosmology and Astroparticle Physics, scientists proposed the idea that the expansion of the universe may be driven instead by constantly merging with other universes. According to lead study author Jan Ambjørn, a physicist at the Copenhagen University, the merging with so-called baby universes, and that a model for this might fit the data better than the standard cosmological model. While the idea of multiple universes interacting with ours isn't new, this study develops a mathematical model to explore the hypothetical impact of this on the evolution of our universe. The researchers' calculations showed that merging with other universes should increase the volume of our universe, which could be perceived by our instruments as an expansion of the universe. The scientists also computed the rate of expansion of the universe using their theory, and their calculations more closely fit with observations of the universe than the traditional standard cosmological model, the researchers said. The author's theory also addresses the problem of cosmological inflation, the mysterious super-rapid expansion that occurred in the early moments of the universe. Physicists have previously proposed that this expansion was caused by the inflaton, a hypothetical field that drove ultra-rapid expansion in the first milliseconds after the Big Bang. But in the new study, the authors suggest this super rapid early expansion could have been caused by our young universe being absorbed by a larger universe. They wrote in their paper that the fact that the universe has expanded in a very short time invites the suggestion that this expansion was caused by a collision with a larger universe. That is, it was really our universe which was absorbed in another parent universe. Since we have presently no detailed description of the absorption process, it is difficult to judge if such a scenario could take place in a way that would actually solve the problems inflation was designed to solve. But one interesting aspect of such a scenario is that there is no need for an inflaton field. The scientists suggested that after being absorbed, our newly enlarged universe then continued to collide with other baby universes and incorporate them as well. Although the author's theory enables us to solve some important problems of modern cosmology, only observational data can validate their hypothesis. Many experiments are currently being carried out to study the properties of the microwave background, so scientists may be able to answer these fundamental questions in the near future. As Yoshiyuki Watabiki, a physicist at the Tokyo Institute of Technology, said, "Our late-time expansion of the universe is different from the standard cosmological predictions, and we believe that observations from the Euclid telescope and the James Webb Telescope will settle which model is best describing the present-time expansion of our universe." Closer to our home, astronomers have just observed powerful glitches in a highly magnetic neutron star, or magnetar, near the heart of the Milky Way. These glitches appear to have massively accelerated the star's spin speed. Plus, fascinatingly, the phenomenon that helps slow down the neutron star, which also known as a dead star after these glitches, could help reveal the star's interior. Understanding what goes on within a magnetar may finally unveil how these strange bodies launch what are known as fast radio bursts, or FRBs. FRBs are mysterious and fleeting pulses of light that can get bright enough to briefly outshine the light of an entire galaxy. Scientists know these extreme, few-second-long pulses exist, but no one has been able to pinpoint precisely why they exist. The Discovery team studied a magnetar that's considered the most active in our galaxy over the last decade, SGR 1935 plus 2154, or SGR 1935. It's located an estimated 30,000 light-years away from Earth and was studied using the Neutron Star Interior Composition Explorer, NICER, instrument aboard the International Space Station, as well as the Nuclear Spectroscopic Telescope Array, NuSTAR, Space Telescope. With these tools in hand, the team spotted two massive glitches associated with the magnetar that were separated by around 9 hours. And according to team member and assistant professor at Paul Sabatier University in France, Sébastien Guillot, the glitches are abrupt changes in the rotation of the star. Each brief observation allows us to measure the rotation speed of the magnetar, and we noticed that suddenly the star was spinning faster than the previous observation. Glitches are commonly observed for pulsars and magnetars, but these are two of the largest ever seen. This magnetar usually spins just over 3 times per second, but the first glitch caused an increase in rotation speed. Then, the second glitch that occurred approximately 9 hours later caused yet another speed increase, 100 times greater than the first. Qin-Ping Hu, research lead and an associate professor at the National Tsinghua University of Education, said that this slowdown occurred over a period longer than the duration of the glitches themselves. Exactly between the two glitches, SGR 1935 launched an FRB, and after both acceleration jumps, the neutron star somehow slowed back down to its normal rotation rate, leaving the team eager to explain both phenomena. Magnetars, like all neutron stars, owe their births to the deaths of once massive stars. After millions of years of burning hydrogen in their cores and converting it to helium, stars that are many times the size of the Sun run out of this nuclear fusion fuel supply. The end of that supply also ends the outward energy flow coming from the core of the star, the force that had been supporting it against the inward force of its own gravity for so very long. As this cosmic tug-of-war ends, with gravity the clear winner, the outer layers of the star are blown apart in a powerful supernova explosion, while the inner core collapses upon itself. This creates a stellar remnant that has between 1 and 2 times the mass of the Sun squeezed into a sphere with a diameter of around 12 miles, 19 kilometers. This is a neutron star. Not only does this entire situation create neutron star matter so dense a teaspoon of it would weigh something like 1 billion tons, but like an ice skater drawing in their arms to spin faster, the rapidly shrinking radius increases the stellar remnant's spin rate. In fact, some neutron stars can rotate as fast as 700 times per second. The collapse also pushes together the magnetic field lines of the dying star, creating some of the universe's most powerful magnetic fields. There are neutron stars out there that boast a powerful magnetic field so intense they qualify for their own category of celestial object. Those are the magnetars. The team behind this research theorizes that the return to normal speed for the magnetar, SGR 1935, is the result of a strong, ephemeral, and magnetospheric wind blowing from the star. Chin-Ping Hu says this wind would carry away angular momentum that rapidly slows the star's rotational rate. As Guillot said, the idea is that the crust of the magnetar would crack under the torque forces at play. This cracking just under the surface of the magnetar releases a huge amount of energy that would locally heat up the surface, sending particles in the form of a plasma of ions and electrons at high temperatures into space at close to the speed of light. The team also thinks the same phenomenon that couples the neutron star's interior with its surface to cause this wind is responsible for the magnetar's X-ray emission being boosted. Potentially, it'd foster the right magnetic conditions for launch FRBs as well. Guillot added that the magnitude of glitches experienced by SGR 1935 could help scientists better understand the interiors of this magnetar and of neutron stars in general. For pulsars and magnetars, the changes in the rotation during glitches are thought to be linked to the presence of superfluid material, neutrons that are not interacting with the rest of the crust and outer core of the magnetar inside the object. During the progressive slowdown of the magnetar, the superfluid material remains at the same rotation speed until the difference of rotation speed between the bulk of the magnetar and the superfluid material is too large. At this point, Guillot explained that the two components of the magnetar combine once more, generating the glitch in rotation, or in other words, the abrupt spin-up of the magnetar. The researcher explained that the next step in the process is to attempt to catch either this magnetar or another one in the Milky Way in the act of burping out an FRB. Anyway, we missed the exact moment of the FRB. But SGR 1935 proves to be quite an active magnetar, and similar bursting activity will likely happen again, and hopefully, next time, we will catch it. The team's research was published in the journal Nature. On Earth, meteorite hunters have just successfully recovered fragments of an asteroid that impacted Earth over Berlin, Germany on January 21st, and the space rocks could be very rare indeed. The 1-meter-wide asteroid, dubbed 2024 BXM1, was spotted by NASA around 90 minutes before it hit Earth's atmosphere. It burned up upon impact, exploding and creating a fireball seen by observers across Europe. Following the event, on January 22, intrepid meteorite hunters were out searching for fragments of asteroid 2024 BX1. One team that hit pay dirt was led by SETI meteor scientist Peter Jeniskens. The crew found the second and third fragments to be uncovered. Notably, fragments of this asteroid have been confirmed to be a rare space rock type that could help shed light on Earth's origins. Thus, studying the remains of asteroid 2024 BX1 might not just be important in understanding Earth's past, but also in safeguarding humanity's future. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.